Next, we're going to have Understanding Hadoop Performance on Lustre. Our speaker is Skory from Seagate. He is a data scientist, senior engineer at Seagate Technology. He's part of the Cloud Research and Analytics Group in Longmont, Colorado, which is part of the Cloud Systems and Solutions Division of Seagate. His responsibilities run the gamut from advanced computer network and system modeling to automatic Hadoop optimization methods, and to lifting servers into racks. Prior to joining Seagate in 2013, he earned a PhD in astrophysics from University of California, San Diego in 2010 by simulating and analyzing star formation in galaxies using the HPC ENSO code. That's a code that we had to suffer with once upon a time. That's heavy duty. And continuing to work along similar directions at the University of Colorado during a postdoc, University of Colorado Boulder during a postdoc appointment. Yeah, I'm sorry if I'm smiling, I'm still thinking about beefs. I apologize.
No problem.
Ladies and gentlemen, Stephen Skory.
Okay, well, thank you for waiting for the last talk. I'm here to talk about Hadoop on Lustre. I'd like to acknowledge my collaborators in name. There's Kelsey, Daniel, Demeter, and Jen. They wish you could be here. Actually, Demeter's here in the back. But I'd like to start off by showing a slide from supercomputing in New Orleans, where we actually had a demo system demonstrating running Hadoop on Lustre. We had a cluster store rack and some boxes, and we actually had a demonstration live on the floor. That's Dan Lingenfilter next to me. So here's a quick overview of the talk. I'm going to talk about why Hadoop on Lustre. We probably know that, so I can skip that pretty quickly. Talk about a Lustre FS plugin, which looks very similar to what Intel just released, but I think you'll like what I say better. Some benchmarks, so this will answer some of the questions that were asked earlier. We actually compare apples to pears. It's almost the same. You can't do exactly the same, but it's pretty close. Then talk about some considerations and how to optimize performance on Lustre. And then talk about Diskless. So we try to do some Diskless optimizations that sound also like what Michelle's doing. We have some benchmarks there. And then some final thoughts. So why Hadoop on Lustre? We probably had already only answered to this, and this is what we covered in the last talk. Basically, you skip HDFS, which is a transfer step. There's lower storage overhead. There's speed. I actually have some plots you can see about speed. You can disaggregate storage from your computation. In typical Hadoop clusters, your computation sits next to your storage. That's the whole idea. But sometimes you want to scale out your storage or your computation at different rates at different times. This is just basically the data movement path. In one choice, you have to transfer into HDFS, do your analysis, and move it out, or you can just keep it on Lustre. We already know this, so I'll skip it quickly. So today, or earlier this week, we announced and we released an open source Lustre FS plugin. It actually looks very similar to what Intel has, but this is free and open source, and you can download it today. It really requires very minimal changes to Hadoop. You can, in fact, run HDFS at the same time as Lustre. I've run jobs from HDFS to Lustre or back and forth. So if your data is already in HDFS, you don't have to abandon that. You can just do both at the same time. You can even keep HDFS on your compute nodes, just like normal Hadoop runs. And the last bottom bullet point is actually false. We haven't issued a PR, but we're aiming to try to get the plugin into normal Hadoop so that you don't even have to, it'll just be there if you want it. So I'm going to show you some benchmarks that we've produced of Hadoop on Lustre and describe the system. We have a rack of HP compute that's actually HP Hadoop compute. So there's 12 cores and 12 hard drives per node. We have 18 data nodes. This is backed by 10 gigabit Ethernet between the nodes. But each Hadoop node also has a second 10 gigabit Ethernet going to the cluster store rack, where we have two cluster store 6000s. And we have enough network bandwidth across all of this that we can basically utilize the Lustre bandwidth fully. So the network's not a bottleneck at all in here. You'll notice that we've got 216 data drives in the Hadoop rack and 160 data drives in the cluster store rack. So we actually have more IOPS, more speed on the Hadoop side than we do on the Lustre side when it comes to just if you wanted to add the hard drives. So here's an actual benchmark showing TerraSort with and without HDFS going to Lustre. You'll see that the blue is the actual timing to run TerraSort, and the orange is the added time if you were to transfer the data from Lustre into HDFS and then do your analysis like you would for some other kind of data flow. So you'll see that and in both cases what we did is we optimized the system, so we tried to get the fastest HDFS and the fastest Lustre. So we're not just, we're not being sloppy. And you'll see that in both cases we get absolute faster performance on Lustre, even with fewer hard drives. So it's the same CPU, same amount of memory, but of course we can run HDFS on one side, Lustre on the other. Oh. We also did some other benchmarks of other popular Hadoop toolkits, and you see in general we're either faster or about the same, so there's really no loss in performance to go into Lustre. And all of these bars do not include file transfer times. So if you were to compare this to HDFS, you might also want to include transferring data into HDFS from Lustre. So now I'm going to talk a bit about what kind of settings your Lustre settings has on, well, actually this plot's a little different. Okay, so this is where I'm looking at stripe settings. And so what you can see is that the stripe size, which is on the x-axis, and the runtime, which is on the y-axis, is actually not very sensitive to the stripe size. If your stripe size is too small, you sort of get not as good numbers, but you can vary your stripe size by quite a bit and get the same answer. It's much more sensitive to how you're running your job, the number of mappers, the number of reducers. So really what this means is that if you have a Lustre system, you can tune it for your other jobs. You can create your directory striping for whatever else you're doing, and Hadoop will run just fine with whatever setting you chose. Played around with RPCs and dirty NV, and you see that this is all within standard deviation of your expected. Hadoop jobs never run exactly the same because there's all kinds of overhead out of orders. And so you see, again, you can just set your Lustre system up, your Lustre clients, for other stuff. Hadoop doesn't really care, which is nice. So here's a plot showing that what I said before is that really, when you want to run your Hadoop jobs on Lustre, you worry about running Hadoop. You don't worry about your Lustre. On the x-axis, we have the number of mappers. On the y-axis, we have the number of reducers. And you'll see we have times in the figure. And you see that as you go above or below the ideal numbers of each, your time increases. And that's typical with typical Hadoop. Here's some additional observations. You can see that with things like TerraSort, we want to tune Hadoop inside of Lustre. Tuning Lustre really doesn't get you anywhere when it comes to TerraSort and likely other IO-intensive Hadoop jobs. So in the case of HDFS, HDFS itself is built on this idea of you take a large file, you chunk it up into blocks, 64 or 128 megabytes, and you distribute them semi-randomly across your cluster. When you run the job, the computation goes to the data, does its thing, and that's how you get your efficiency because the data doesn't have to move again. But what it means is that when you upload your data to HDFS, you've chunked it. You said, I'm only going to work at 64 or 120 megabyte chunks. With Lustre, you don't have to decide beforehand what size chunks. You can just take your data and then maybe tune your job to the CPUs you have. So if you add more CPUs, you can add faster processing. We have seen that Lustre does better with fewer writers than a similar job with HDFS. So in this cluster, again, we have 216 cores. We found that we wouldn't want to run with the full number of reducers that we could actually support with a number of cores when writing to Lustre. On HDFS, we'd actually get better performance with more reducers. So slightly fewer writers works better. Again, with a typical Hadoop cluster, for sort of average, you don't know what you're going to be doing on this cluster, you do 1 CPU core per hard drive. HDFS is not rated, so it's just a single block device and works out. That's the sort of simple rule of thumb. With Lustre, you don't have to do this. You can just scale them whatever you want. But finally, the procedure and some of the heuristics for tuning jobs off of Lustre is pretty similar to HDFS. Focus on your number of mappers, number of reducers, maybe some of the more commonly cited. Just search on the internet, search for Hadoop tuning. A lot of those same parameters will help you get good performance when you're doing Hadoop on Lustre. So now I want to turn tables to another thing we tried with Hadoop. We call this the Diskless modification. So all of the previous benchmarks I'm showing you, these were nodes that had local disk. This was an operating, the OS disk, but we also used the local disks for shuffling local data for temporary storage of the MapReduce process. Beginning a few years ago, DesireText, that of course we purchased, started looking into a modification of Lustre where you wouldn't need local scratch disk for the MapReduce shuffle. And they put out a white paper in 2011. Finally, we actually released the source code for these changes last year. They're on GitHub, the same place you can find the Lustre FS plugin. And so I'm going to talk about our experience with this attempt at optimization. So some of you may not know some of the really gritty details of MapReduce, but I'll not really get that deep. But the key thing is this plot shows you how the data moves in a normal default Hadoop system. We take data off of HDFS, which is distributed through triple copy. You run your mapper, which then stores the output on local disk in blue there. Then using HTTP, you transfer the data to the reducer, which if there's enough RAM, it can do things in RAM. If it doesn't have enough RAM, it does things back to local disk. And then finally, it writes things back out to HDFS, including 2 more copies that will go across the network. So typically, your reducer will write to the HDFS store that's on the node with data computation, but then 2 more copies go out after that. So here's how it would look on, this is how it looks on Lustre. We pull data off of Lustre, the mapper stores data on local disk. Again, we shuffle, maybe store in memory, store on disk, and then finally we write back to Lustre. But only 1 copy. Of course, the copy goes over the network, but it's only 1 copy as opposed to 2 copies in the case of HDFS that goes over the network. What this idea is that if we don't have local disk on the compute nodes, we can store the shuffle data on Lustre. But because it's already on Lustre and all the nodes can see Lustre, we don't actually have to make a copy. We can skip a step. We can tell the reducer, hey, you don't actually have to transfer HTTP. You can just go get it directly off Lustre. And so this is what we implemented. And my picture is not coming through. But the numbers are there. So what you see is that we actually get slower speed with the modified code, with decently sized terasorts. And we were wondering why. I'm sorry, my picture isn't coming through. I don't know why. But the answer is that, oh, here we go. So what happens is we, of course, have the Linux I/O cache. And if you're storing the data on Lustre and you're telling the reducer, go get it from Lustre, it has to go read it off of usually a spinning disk and get it across the network. Remember, networks are fast enough that we're not network bottlenecked. But if you go and ask the mapper side, the computer that ran the mapper, there's a very good chance that a good chunk of that data that's already been written to Lustre will be sitting in the RAM cache. And when you go ask the mapper computer, can you give me that file? It can just pull it out of RAM. And we ran some tests where we actually turned off the RAM cache. And the storing the temporary data on Lustre method actually then becomes faster. But that trims everything slow, of course, because the RAM cache is very useful. So my final thoughts is that we've tried 3 ways of running Lustre, putting on Lustre, and we see that the best way is you want to have at least some local disk on your compute nodes. It doesn't have to be super large. We actually have played around with SSDs, and we found that it's not super, doesn't really help you that much. So that really it's best to just go with a hard drive. That if you're going to do diskless, so you're going to have diskless nodes, and you have to store intermediate data on Lustre, don't modify the code. Just do the normal shuffle, because then you can take advantage of the Linux RAM cache. And finally, thank you to my collaborators. Any questions?
So if I understood you correctly, you said that the cold cache read from Lustre that you need on the reducer, makes the performance disappear rather than going to temporary storage. But you said that you could ask the mapper for that data. Have you given any thought to how you might read from that hot cache on the mapper?
So people have done things like that. There's a group at Ohio State, DK Panda group, that's doing RDMA to help accelerate things like that, where actually the mapper side will actually send the data directly to the reducer instead of sort of pre-sending. But we haven't really played with that too much.
So did you look at the OSS read cache, if that could help you?
No, we haven't. Thank you.
Thank you very much.